Okay, so welcome to the oral session of Human Behavior Understanding 2021. So we have like 4 papers in this session, and like we will have like the pre-recorded like talks from each of these authors of the papers, and then we'll have questionnaire session. So we can post our questions in the chat box and like feel free to like post your questions. So without any further delay, like I'll play the first video of the paper titled Context Aware Personality Inference on Didactic Scenario, introducing the Udiva dataset. So I'll share my screen. Oops. So let's start from the beginning. So my screen is visible, right?
To present this joint work called Context-Aware Personality Inference in Dyadic Scenarios, introducing the Udiva Dataset. In dyadic interactions, we use verbal and nonverbal communication channels to convey our goals and intentions while building a common ground. Both interlocutors influence each other based on the cues we perceive. However, the way we perceive, interpret, react, and adapt to them depends on many factors. For instance, our personal characteristics such as personality, culture, mood, and other socio-demographic or physiological factors. And also other shared factors such as the shared history, characteristics of situation and task, even the environment. Also, to analyze individual constructs during a conversation, such as emotions or personality, both interlocutors should be jointly modeled due to the existing dyadic interdependencies. The importance of dyadic interaction research is demonstrated by the large number of public audiovisual datasets that have been released during the last 2 decades. Some of them just focus on isolated recognition of dyadic actions. Others focus on emotion recognition in conversations. There are other datasets that focus on specific applications or dyadic constructs, such as mimicry. There are many datasets that focus on analyzing verbal cues from conversation. Finally, there are some general-purpose datasets aimed to understand human-human interaction in a more holistic manner. For instance, we identify some of them that are focused on parental interactions. Very few include specific information about the participants, such as socio-demographics or personality, or even the characteristics of the interaction, which are also very important to really understand interaction. Apart from this lack of context annotations, most of the datasets are also limited in terms of the number of participants, recordings, views, language, or purpose. In order to fill this gap, today we briefly introduce the Udiva dataset, consisting of time-synchronized multimodal based on free and structured tasks performed in a laboratory setup. Here we explain some of the highlights. The dataset includes 188 dyadic sessions with 147 participants from 4 to 84 years old. The dataset includes up to 91 hours of dyadic interactions with an average of 2.5 sessions per person. Participants come from 22 different countries, being Spanish the majority language of interaction, followed by Catalan. This is the first public dataset of these characteristics, including these 2 languages. The dataset was recorded using 6 third-person view cameras, 2 egocentric cameras, 3 microphones, and 2 heart rate monitors. Currently, the dataset includes socio-demographic data, pre- and post-session mood and fatigue level, self-reported and perceived personality using validated questionnaires, and the type of relationship among interactants. We are currently gathering more labels in order to analyze the interaction in a more holistic manner. Each dyadic session is divided into 5 different tasks. Here we explain 4 of them, which are the ones that are going to be used in the subsequent analysis. The first task is always talk, which is basically a free conversation and is delivered first as a warm-up. Then the 3 remaining ones are delivered in a randomized way. First, we have Lego building, which is a collaborative task in which participants had to build a Lego together following the instructions leaflet with 4 difficulty levels. Then we have the animals game, in which participants had to ask 10 yes or no questions each to guess the animal they have on their forehead with 3 difficulty levels. And finally, we have a ghost game. This is a competitive game in which participants had to compete against each other to select the correct figurine based on the contents of a given card. As an initial analysis on the Udiva dataset, we present a novel method for self-reported personality traits inference, which is one of the key elements to develop user-tailored intelligent systems. As input, we use the frontal cameras of the dataset, capturing a target person and the other interlocutor during the dyadic interaction. We also include metadata information about participants and the session. More specifically, we differentiate among 3 different types of contexts. First, individual, containing age, gender, cultural background, session index, and pre-session mood and fatigue values for a given person. Then, session context, containing the order of the task within the session and the difficulty of the task. And finally, the dyadic context, telling us whether the interlocutors knew each other or not before the session. We gather all this information into 2 different types of metadata. Target person metadata containing individual and session information, and the other interlocutors metadata containing individual and dyadic information. And finally, we also include the audio signal of the scene. As output, of course, we use the regressed self-reported Big 5 ocean traits of the target person. For the method, we use a repurposed action transformer network to take advantage of the context around the target person when regressing personality. Each task video is divided into 32 frame non-overlapping chunks, which is equivalent to 2.5 seconds. This means that inference is performed per chunk, and then the final prediction per person is computed as the median of per chunk predictions per person. One of the characteristics of transformers is the selection of query keys and values. Here, we select them taking into account that for each unique interaction, we have the following pieces of multimodal contextual information. The query can contain the target person face chunk, which is extracted from the target person view, and also the target person metadata. Then, for keys and values, we differentiate among local stream and extended stream. The local stream contains information from the target person, specifically body, gestures, and scene, and also include the audio. And finally, for the extended stream, we include further information from the other interlocutor metadata, and the audio. This allows the model to consider both intrapersonal and interpersonal influences during a chunk. In this slide, we show the personality inference pipeline. First, we extract features from the input streams using pre-trained networks. Then we compute the spatiotemporal encodings and include the multimodal information to finally have the local information and the extended information. Here we have the transformer layer, which includes 2 different transformer units, one for the local information and the other for the extended information. These units combine this information with the query, and the output is an updated query which is fed to the next transformer layer. In our case, we use 3 transformer layers. The output is the final per chunk personality traits prediction. For the experimental evaluation, we selected a subset of the whole dataset. In particular, we take into account participants aged 16 years and above, for which Big 5 personality traits were available. As for the other ages, we used other validated questionnaires, depending on their age. In order to compute the splits, we use a greedy optimization algorithm to find the best split so as to avoid repeated participants between splits and respect the data distribution as much as possible. And then we train 1 model per task, since each of the 4 tasks can elicit different social signals and behaviors, which in turn can be correlated to different degrees with distinct aspects of each personality trait. Here we can see the distribution of the final splits for train, validation, and test. They are subject-independent splits. We experimentally evaluate the contribution of each additional input incrementally. On the left, we will show the type of input used for a given experiment. On the right, we will show the average results per task, and on the lower side of the slide, we show the results per trait and per task. All results are reported using the mean square error. We start with the baseline, computed as the mean of the portrayed ground truth labels of the training set. Models like this tend to predict the mean of the training set. The challenge is to get the network to properly model values that deviate from the mean. We will see that the more information we include, the better. Here, on average, only talk benefits from the addition of the extended visual context, which appears to be harming the prediction performance for LEGO. This can be attributed to the fact that the interaction during this type of collaboration is more slow-paced than in other tasks. Therefore, interpersonal influences cannot be properly captured during just one chunk. In contrast, for more natural tasks, such as talk, there are many instant action reactions that can be observed during a single chunk, the effect of which is reflected with improved results for those tasks. And we continue. The inclusion of all the available metadata validates our intuition that personal, task, and dyadic details provide relevant information to the model to produce overall better results. If we compare LE to LEA, better results are obtained on average for all the tasks when all the information is considered, which is in line with previous literature. However, the observed improvement is smaller for LEGO. One plausible reason would be the noise produced by the LEGO pieces when being moved, or the instruction book while turning its pages close to the microphones, which would interfere with the learning process. Finally, in the last experiment, the model is aware of the overall contextual information. And we noticed that apart from LEGO, for which the audio dropbacks were already commented, all the other tasks seem to benefit from the provided knowledge, obtaining the lowest error value on average. In this paper, we have introduced the Udiva Dataset, which is currently the largest multi-view audiovisual dataset of dyadic face-to-face non-scripted interactions. The dataset will be publicly released this year. We have also proposed a multimodal transformer-based method to infer the personality of a target person in a dyadic scenario, using both interlocutors' information along with audiovisual, scene, and task information. Finally, we have incrementally combined the different sources of context, showing consistent improvements when using all available context information. Thank you for your time, and I'll be happy to answer your questions.
Okay, so time for the questions. Do we have any questions?
I have one question. Hi, Christina.
Hi.
So we assume normally that the personality is a stable construct. So is there, for example, in your experimental protocol, something that allows us to test whether the personality results that we're getting is consistent over time? For example, like, you know, analyzing a part of the person's data and then an unrelated part, and then seeing whether the models give us the same kind of results.
Yeah, so that's a very good question, and that's part of our future work. We didn't get to do that for this paper. But yeah, definitely, that's one of the things.
And the tasks that you're using 4 different tasks, right? And are they sufficiently different from each other, for example, in generating different emotional states? Because, for example, if a task is very funny and if people laugh all the time, then, you know, an apparent personality estimator may decide that they're agreeable people or they're extroverted people. But if it's a very serious task and then you have to have, you know, a high concentration, then they may decide that you are conscientious, for example. So across tasks, if the predictors can predict the same values, that would be really nice, right?
Yeah, it would be really nice. So in the talk task isn't the one that we see most variability in, because so people talk about many different things, some sad stories, very funny stories. Yeah, it depends on the person and the context, of course. For Ghost, we see people that get very angry because they cannot perform the task correctly, or so the other person is better at the task than them. For the others, for LEGO, we don't see much difference. But we do see that, so people came voluntarily, but so some people, most of the people came voluntarily, but some people came not forced, but like they are students or people that we know, and we tell them, please come because we are doing this, we are recording this data set, right? So you can see some people that are like completely bored the whole time, or very happy because they are very extroverted and they agreed to come. So regardless of the task, you can see these differences in personality as well, or yeah, personality in this context, let's say. But yeah.
Do you have any more questions?
Okay. Yeah,
yeah,
maybe I have one. So thank you for the interesting presentation. So I was just wondering more from a technical point of view. So the entire data set, I think, is 90 hours or something like that, right? So that's quite a lot of material. So do you have any experimental protocols, so fixed tasks attached to that, that you plan to, let's say, when you release the data set, to give out to the community? Because I would imagine if just the data set itself it's really huge, right? So just in terms of processing all the materials or all the videos, deciding which parts are important. Also in your example, for example, you had one phase, the other one was context, and so on. So can you say something about the experimental protocol that you plan to attach to this, if you have any, and the processing that's required in terms of, let's say, time to solve one and train for one of these tasks, because it seems enormous. So.
It is. That's why we haven't released the dataset yet. So the dataset was recorded early 2019. So we are working on the post processing and deciding which are the best splits. Of course, we may have for different tasks. For instance, for this specific task of personality inference, we wanted to have subject independent splits, and that was a bit complicated because people could appear in, so people could repeat the experiment up to 5 times, which means that they interact with many people, and if we want to have a subject independent split, we need to remove sessions, but we need to preserve the data distribution as much as possible. So that was some months of work, and that's only for personality. We are planning also, so the one that we are preparing now, it's for action detection and intention detection or anticipation. That would require more, so some research, of course, of how we would, what's the best split, let's say. We don't have an answer yet, and that's what we are doing. So yeah, maybe in the end, we would have either the different splits per task, or yeah, that's work in progress. It's a huge amount of work, as you said. Yeah.
Yeah, I imagine, because organizing and structuring such large data sets is really challenging always. Thank you.
Yeah.
Okay, so we can continue to the questions, in the post your questions on the chat box, and Christina can reply there. Thank you, Christina, for your nice presentation. And let's rounds of applause, and let's go for the next presentation. So which is titled Person Perception Bias Exposed, Revisiting the Fast Impression Datasets. So I'll start to share the video. Just 1 minute.
Hi everyone, I'm Júlio Jacques from University Alberto de Catalunya in Computer Vision Center. I'm going to present our work person perception bias is exposed, revisiting the first impressions dataset. Imagine that pairs of short vids are given with people talking to the camera about any topic. As an annotator, you are asked to define which individual in a pair looks more friendly or maybe more organized. Then you may start analyzing people's behavior and their attributes in order to build your first impressions. At the end, your choice might tell something about you. However, the overall perception given thousands something about the database. The study of human personality became an attractive research area in visual computing, given the vast number of scenarios it can be applied. While real personality can be assessed through self-report questionnaires, apparent personality assessment is given by external observers. This subjectivity makes the task of creating automatic methods for personality perception challenging, since the bias will be reflected on the annotations. The use of pairwise comparisons can reduce perception bias produced by absolute annotations. However, completely eliminating it is extremely difficult. This work revisits the first impressions database. We analyze for the first time the original pairwise annotations and reveal existing perception biases associated to gender, ethnicity, age, and face attractiveness. We further show that the mechanism used to convert pairwise annotations to continuum values may magnify the bias. The findings of this study are relevant for the computer vision community that is still creating new data sets on subjective tasks and using them for practical applications, ignore these perceptual biases. Fairness-aware machine learning approaches can be categorized as reprocessing techniques, which aim to modify the input data, algorithm modification, which modify existing algorithms by adding constraints or regularization, post-processing techniques, which modify the output of an existing method to be fair. These categories, however, consider the data is already available and ready to use. Our work goes one step back and analyze how perception bias affect data labeling, which aligns with the idea that unfairness induced by unmeasured predictive variables should be addressed through data collection. From a computational perspective, most works study the general bias problem, such as imbalanced training data, covariate shift, or sample selection, which can be found in almost any machine learning-based task, while little attention is given to subjective bias analysis beyond the perspective of explainable models. Although pairwise comparisons can reduce the perception bias in annotation tasks, this work shows that people's attributes combined with annotators' bias can have a strong influence on data labeling, suggesting that future works on that topic need to pay attention to the way the pairs are defined and presented to the annotators, since the pairs themselves can also be a source of bias. The first impression dataset is currently the largest and public dataset developed to advance research on automatic personality perception. It was originally annotated with the big 5 apparent personality traits: openness, conscientiousness, extraversion, agreeableness, and neuroticism. Later, it was annotated with an invite to interview variable, aiming to advance research on explainable machine learning. The dataset is composed of 10,000 short videos of people talking to the camera. Gender and ethnicity labels are also provided. Overall, it's more or less balanced with respect to gender. However, it is extremely imbalanced with respect to ethnicity. It has around 345,000 annotated pairs. Table 1 shows that data imbalance is strong with respect to different subsets, which impose another obstacle in addition to perception bias, when the goal is to build fair machine learning methods. The pairwise data was converted to continuum values by fitting a broadly loose model with maximum likelihood, which were further scaled to be in the range of 0 and 1. This way, each video sample will have a continuum value associated to each trait dimension. The image shows few individuals with high and low values for a particular trait. As mentioned before, Our work partially relies on automatic methods to extract face attributes, to remove any bias caused by the imbalanced ethnicity category. First, a force detector is applied on each video at 5 consecutive frames. Then, face attributes are extracted using a modified version of VGG16 that regresses either the attractiveness score or the perceived age. Finally, the per frame predictions are averaged per attribute. On top, we show the distribution of face attributes extracted for the Caucasian individuals in the dataset, and some prediction results at the bottom. It must be emphasized that the aim of our work is not to advance the state of the art on face attribute recognition. Prediction attributes are taken as soft labels and used as proof of concept. Next, we analyze perception bias associated to gender and ethnicity, obtained directly from the pairwise labels, and show that some of them are amplified when converted to continuum values. To measure the bias present in the continuum values, we compute the number of cases where individual A obtaining a higher value than individual B, given a particular trait and subset. Overall, the analysis will show that some groups of individuals were perceived differently, in some cases, as a function of their attributes. Table 2 shows the percentage of individuals perceived as being a more or less representative sample for a particular trait, considering the gender only. The analysis considers the subset of pairs where individuals have different gender, taking into account the pairwise labels on top and continuum values at the bottom. As it can be observed, there is an overall bias toward women. Moreover, we can also observe that the differences are amplified when the data is converted from pairwise labels to continuum values. Table 3 shows that gender had stronger influence than ethnicity when Asian versus Caucasian subset was considered, and that there is an overall bias toward the women, highlighted in red. Table 4 and 5 show that ethnicity had stronger influence than gender when subsets Asian versus African American and African American versus Caucasian were used. That is, Asians and Caucasians were more frequently perceived as being a more representative sample for a particular trait compared to African Americans, independently from the gender of individuals. Next, we present the analysis of face attributes and their influence on data labeling. To remove the gender variable from the analysis, only pairs of individuals having the same gender are considered. Figure 6 shows the number of times an individual in a pair recognized as more attractive was chosen, divided by the number of times an individual recognized as less attractive was selected, varying the face attractiveness difference between them. If face attractiveness have no influence, the ratio would be 0.5. Values higher than 0.5 show a bias toward more attractive individuals, whereas values lower than 0.5, the opposite. As it can be seen, when face attractiveness difference between individuals increase, there is a higher fraction of individuals recognized as more attractive being perceived as a more representative sample for a particular trait, suggesting that face attractiveness is biasing the annotations. This trend was observed to be stronger for some traits, and even stronger when both individuals being observed are women. Figure 7 shows the number of times an individual in a pair perceived as older was chosen, divided by the number of times an individual perceived as younger was selected, varying the age difference between them. If perceived age had no influence, the ratio would be 0.5. Values higher than 0.5 show a bias toward older individuals, whereas values lower than 0.5, the opposite. As it can be seen, annotators had an overall bias toward older men, except for openness and extraversion traits, especially when age difference between individuals increase, and a bias toward younger women most of the time and for all dimensions. suggesting that the perceived age attribute influenced data labeling in different ways. This work used the first impressions dataset as case study to expose how perception can influence data labeling of a subjective task like personality. We analyzed for the first time the original pairs provided with the dataset and revealed the existence of different types of bias. After analyzing the pairwise-based annotation setup, our study suggests that new protocols need to pay more attention to the way the pairs are defined and presented to the annotators, since the pairs themselves can be a source of bias. Moreover, our perception is dependent to the observer. The analysis and correlation of attributes between annotators and people being annotated could explain how some bias are produced. However, this would require a dedicated discussion around privacy and ethical issues that goes beyond the scope of this work.
Thank you. So time for like the questions. Do you have any questions?
I have one.
Mm-hmm. Yeah, Albert, go ahead.
Yeah, Julio, in the IEEE transactions effective computing paper that summarized the first impressions challenge, there was a figure that showed that while the database annotations did not show a strong bias against females in the invitation to interview variable, when you combined it with age in the analysis, there was a very strong bias in that younger females were invited for the interview and older males were invited to the interview. So they had, on the average, they had similar distributions, but the distributions were skewed in different ways. Did you also look at age as a differential factor in the other analyses that you have conducted in attractiveness, for example?
Hi, thanks for the question. Actually, we analyzed the perception of age in the pairwise, not directly in the continuum values. If I'm not wrong, the paper you are mentioning, the analysis was about the continuum values, and here we are analyzing the pairs. So given a pair of individuals or videos, which individual were most frequently perceived as being more extroverted or would be invited for interview most of the time. So this is more or less, they are similar because we are showing there are bias in the pairs. And I imagine that the bias are more or less similar to the ones we have in the continuum values. Although we also observed the bias are somehow amplified when converted from the pairs to continuum values. Yes.
Let me say one word about this. Actually, what we saw is that when we computed the continuous values, it had a high agreement with the labelers, but the continuous values were amplifying a little bit the perceptual bias already included in the pairs. So what we did now with this analysis of the bias is to show which were the exact bias that having in the data from the original pairs. And when we compare them with the continuous values, we showed that the continuous values were amplified. But Albert is right that this combination of variables to see their influence has not been analyzed in the current paper. So this is a good suggestion. So we found differences in the perception from the pairs and the continuous values, but we have not done this combinatorial analysis of the bias, putting together age with the other, because we did so many analyses that we thought it was a lot. And when we started to do this combinatorial, then the significance was smaller, also because the set of data were significantly reduced, you know. but this is a good suggestion.
Thank you.
Okay, so we'll thank Sergio and like the speaker, Julio. So we'll head to the next presentation. And like the title of the presentation is Crick and Jest, estimating the player's level of experience from board game behavior. So I'll start to play the video. Oops. Well, just bear me for a second. Something is wrong. Sharing the screen. Share screen. Oh.
Hello everyone, my
Can
name
you
is
share?
Olanuyi.
Is my screen visible, right?
Yeah, it's fine.
Yes, it is.
Okay.
I'm a graduate student of Artificial Intelligence at Utrecht University in Netherlands. Today, I'll be presenting our paper titled Geeks and Guests, Estimating Players' Level of Experience from Board Game Behaviors. Various studies have come up with certified questionnaires that can be used to measure certain social and psychological constructs in participants. However, the use of these questionnaires come with their fair share of challenges. This calls for the need of methods that can automatically estimate and analyze these behaviors. In this study, we automatically evaluate the level of confidence and anxiety of participants while they play a board game. We ask the question, can visual cues made by participants during critical game events say something about their anxiety and level of confidence? We define visual cues as facial expression made by participants. In the slide, we see an example of two participants. The first participant shows a confused expression, and the second shows a bored expression. We classify facial expressions into three categories. One, the positive expression. The third, the focused facial expressions. We define the critical game events as activities in the game that are crucial or define how the game is to be played. Naturally, we would expect that geeks who are used to board games would show more confidence and less anxiety as opposed to guests with little to no board game experience. The novelty of this work lies in the use of facial expression during board games to estimate internal properties such as anxiety and confidence. We also propose a new method that uses the facial expression of both the interactor and the interactee in a dyadic interaction setting. We define the interactor as the person who initializes a critical game event, and the interactee as the person who receives or who is on the other end of this initialized game event. The Mumbai Data Set was extensively used in this work. Our data consists of 39 recorded Magic Maze game sessions with 57 distinct participants within the age groups of 15 to 43. Participants were asked to report their level of experience at board games, and we then grouped them into the inexperienced group, which consists of participants with experience level of 0 to 1, and the experienced group, which consists of participants with experience level of 2 to 4. We also make use of facial expression annotation, which is found in the Mumbai data set. On the slide, we can see an example of two participants who are smiling, and their corresponding annotation is the positive expression. the methodology pipeline. In addition to the annotations gotten from the Mumbai Data Set, we also created a critical game event annotation. Using the questionnaire as an annotation, we extract two groups of features. The first group is used for the correlation analysis. These features include the count, average, and standard deviation of each facial expression displayed by participants during and outside critical game events. We then test for a correlation between each feature and each dimension for both of the questionnaires, that is, the game experience questionnaire and the personality questionnaire. Next, we make use of the open face features of players during the critical game event to predict the player's level of experience. We apply three methods for this prediction. The first method is the single source, single output method. The second method is the multi-source, single output method. And the third is the multi-source, multi-output method. In the single source, single output method, we create two distinct classifiers. The first classifier takes the open face feature of only the interactor and predicts the level of experience of that interactor. The second does the same thing, but now we do it for the interactee. So we take the facial features of the interactee and predict the level of experience of this interactee. For multi-source single output, we also have two distinct classifiers. The first classifier uses both the facial open face features of the interactor and the interactee to predict only the level of experience of the interactor. And the second uses also both their facial features, but to predict the level of experience for the interactee. With the multi-source, multi-output method, we have one classifier. This classifier takes the open face features of the interactor and interactee and predicts both the level of experience of the interactor and the interactee. Correlation analysis results. With the correlation analysis done against the game experience questionnaire, we observe a positive correlation between the count of positive expressions displayed by players outside a critical game event and the tension dimensionality of this questionnaire. According to the design of the questionnaire, tension is not associated as a negative effect. And this is easily noticeable in the game since it is a cooperative game, and the most tension players experience is when they notice they are almost out of time and they are losing. The reaction we observe is that players are smiling and grinning at the fact that they are about to lose. This relates to the nature of the game and also shows how the rules of board games can be used to evoke or suppress certain emotions. The other correlations observed from both the game experience questionnaire and the personality questionnaire shows that the facial expressions during this critical game event could carry useful behavioral signals. The experience level prediction. We use a decision tree as a classifier to predict the player's self-reported level of experience. According to the results displayed on the screen, we see that the single source, single output method worked better at predicting the interactor's level of experience. However, this is not so for the interactee. The multi-source, multi-output method worked best at predicting the interactee's level of experience. This could mean that by studying the facial cues of the interactor and interactee in dyadic interaction settings, we could get better insight into behavioral cues of the interactee. In conclusion, by analyzing facial cues during critical game events of a board game play, we were able to measure the anxiety and confidence level of players by predicting their level of experience. For further studies, body motions and gestures of participants during game events can be added as features for the classifiers. This is because we observe that participants make body gesticulations during these critical game moments, and this could include rich behavioral cues. We also know that the decision trees are a relatively simple classifier, and by applying temporal classifiers, better prediction and insights might be gotten. Thank you very much for listening to this presentation. You can now ask your questions.
Okay, time to questions. If you have any questions. Okay, so if you don't have any question, I have just short questions. Like, so you have used like all the features from OpenFace, or like what are the features that are particularly being chosen?
Okay, so in the Mumbai data sets, they already did a summary of the different open face features, and they used, I think, the gaze direction, action units, and facial landmarks. So we use those exact same features as well, since these are action points within the face that are used during facial expressions. And also they summarize the entire videos using like first and second derivative so as to reduce the number of frames, which we also use for classification as well. So we got that from the Mumbai data sets.
Okay, and all the set of features like for gauge or the pose.
Yeah.
Because they have different set of features, right? Like I think like all some dimensions.
Yeah, that.
Okay.
So
okay, thank you.
Yeah. I have a quick question. So you were estimating players' experience in critical moments. So how did you define these critical moments? What defines a critical moment in the game?
Okay, so for example, we made use of the Magic Maze board game, and critical game moments serve as rules or things that are very particular in how the game would be played. In Magic game, it's a non-verbal game, so participants are not allowed to talk for most of the game. However, they can use a red cone to signify to another participant that they need them to do something. So in this case, the red cone serves as a major means for communication amongst the participants. So we make use of this moment as critical game moments because it is a moment of interaction. So this could be also other rules in board games.
So what's then the duration for estimating? So I guess it's video, right? So it was from video, not static images.
Yeah.
What's the duration of, or the average duration of such an critical moment? So did you then split up a game into chunks of critical moment and then report it for each one, or was that combined for a whole video but just analyzed for based on, let's say, 10 critical moments in a game?
So we split the video into 50 frames, so overlapping frames of 50 frames, because the shortest duration of facial expression lasted within this 50 frame moment. So we had multiple classification within all the frames that fall into the period where the critical game events occur. So on top of doing this, we now did like a majority voting where we take all the frames that fall into a critical moment and select the most voted level of experience from the classifier, then compare to see if like there is like a more accurate predictions based on this voting system.
And so the experience was just two classes, experience, not experience, or was it more?
Yeah, so we made it a binary classification.
Okay, thank you.
Thank you.
Okay, so let's thank the speaker and move ahead for the next presentation. So which is like post-based sign language recognition using GCN and Badit. So we'll go for the next presentation and let me share the screen. Okay.
On post-based sign language recognition using graph convolutional networks and BERT. Sign language recognition problem. Given an input video with the signer performing an American Sign Language sign, we have to predict the class from it. Signaling a sign language word requires very subtle body movements, which makes a sign language recognition a challenging problem. In this work, we utilize information from human skeletal motion for sign language recognition. In our approach, We capture spatial and temporal information separately and perform late fusion. Our proposed architecture captures the spatial interactions in the video using a graph convolutional network. The temporal dependencies between the frames are captured using BERT. For spatial modeling, we extract the poses from frames using OpenPose. We represent the pose using 13 upper body key points and 21 key points for each hand, a total of 55 key points. We represent the human body as a fully connected graph, which allows us to express the relative positions of various body key points as an essential part in order to predict the glass. The key points are the nodes in the graph. The edges are weighted and learned during the training process. The node representations are updated using the update rules given below. In the update rules, H stands for the representation of nodes in the Lth layer. W stands for the weight matrix in the Lth layer. A is the adjacency matrix. Sigma is the nonlinear activation function, tan H. Multiple layers are stacked on top of each other to constitute one graph convolutional network block. The updated node representation includes spatial information of all the key points and interactions between them. We stack multiple GCN blocks on top of each other and provide residual connections between the stacked GCNs. This completes our spatial modeling module. Recently, architectures based solely on multi-head self-attention have achieved great results in sequence modeling tasks. We use one such architecture, bidirectional encoder representations from transformers, BERT, for temporal modeling. The embeddings for each frame form the input of the BERT encoder. The input is concatenated with learned position embeddings to capture the positional information, and the input is padded with a classification token. The corresponding output from the last layer in BERT, YCLS, is passed through a fully connected layer and is eventually used for predicting the gloss. In our proposed architecture, we randomly select 50 consecutive frames from a video and use the poses in them as the input to our architecture. The spatial module and the temporal module are same as previously described. The output from the BERT, YCLS, is passed through a fully connected layer to project it into a G-dimensional space, where G denotes the number of classes. Similarly, the output from GCN is projected into a G-dimensional space, and a skip connection is provided from the output of GCN to the output of the BERT. The resulting output is followed by a softmax layer to predict the output class. We use standard cross-entropy laws to train the network. We use the word-level American Sign Language dataset to validate our results. The dataset has been recently introduced and supports large-scale word-level sign language recognition. The videos contain Native American Sign Language signers showing videos of a specific English word in American Sign Language. WLASL 100 contains the top 100 words in the dataset, and WLASL 300 contains the top 300 words in the dataset. We use top 1, top 5, and top 10 accuracies to evaluate the model. Our model achieves a top 1 accuracy of 60.15% on WSL 100 and a top 1 accuracy of 42.18% on WALSL 300. The table shows a comparison of our model with existing post-based architectures. The results show that modeling spatial and temporal information separately and explicitly with GCN and BERT respectively improves the prediction accuracy. This slide shows frames of various videos along with their ground truth and top 5 predictions by our model. Though our architecture only uses poses, we use RGB frames here for better understanding. As we can see, for predicting the word doctor, the model is able to capture the temporal dependencies accurately and even able to grasp the slightest movements in hand. As we can see from the first row in both the images, the signs for words Halloween and headache are very similar and can be confused even by a human. So it is natural to expect the model to confuse between them. For this sign back, given that the signer is slightly rotated in the frame, it is hard to differentiate between the poses for the words back and candy. Also, in-plane and out-of-plane movements are not being differentiated by our model, since we are only utilizing two-dimensional spatial information. Further, we observe that increasing the vocabulary size, that is the number of classes, leads to a fall in accuracy. This happens because the dataset contains ambiguous signs and their meanings depend on the context. Increasing the number of classes also increases the number of such ambiguous signs, leading to a fall in accuracy. Our work addresses the fundamental challenge of sign language recognition in order to bridge the communication barriers between hearing and vocally impaired people and rest of the society. We propose a novel post-based architecture for word-level sign language recognition, where we model spatial and temporal information separately using GCN and BERT. In our future work, we plan to utilize the three-dimensional spatial information. Also, we plan to include image-based features into our model. Thank you all for your time.
Okay. So still we have some illustrations. Okay, so time for questions. Yeah, sure. How about?
Vito, go ahead first, please.
Yeah, thanks. So thank you for the interesting presentation. I have just a question. So when you look at these data sets and the experiments that are done, you report quite a solid performance. But I was wondering, how do these kind of models generalize to more unconstrained settings? So I guess you cannot always assume that someone will be in front of homogeneous background, right? So for certain applications, you probably can. But I guess the ultimate goal here is to deploy these methods for also in more unconstrained settings. So what would be the applicability of such models to such data characteristics? So would they work? What do you see here as the main, let's say, difficulties in applying them to such data?
So you're basically saying that in the real world scenarios you would have varied backgrounds. So would the model work in such cases?
Oh yeah, of
yeah,
course.
and also we can have like
different characteristics. It could be more unconstrained. So it could be some sort of occlusions, maybe some poorer quality data in any aspect. So how would the transition to more unconstrained settings affect the model? So where you see the main difficulties with that?
So the main difficulties would be like since we rely on a post detection network. So if we have occlusions, like the input the poses won't be proper. So we might have issues. And to comment on that, we only tested on the data set and we haven't tried in the wild. So it's hard to say what exactly. But with the poses, that's going to be the challenge.
So basically, the first building block in that pipeline needs to be improved to be applicable to more challenging environments.
Yes.
Okay, thank you.
Yeah, Alva.
So the newer databases for sign language recognition propose continuous settings, first of all, like, just in conversational translation of, and then talk about vocabularies in the order of 15,000, 16,000 words. So I was wondering, how do these individual sign-based approaches generalized to continuous settings when the number of words are so large that an individual classification becomes very difficult?
I think sorry, go ahead.
Well, in the continuous setting, the other thing to consider is the context of it. So which our model doesn't address it now, the context aware prediction. So that part of it is not done in our current work, and we are trying to do that in our future work about using the context information too.
Mm-hmm. And do you think like depth informations can help into like splitting out these confusions, right? Like in the last slide, as you shown, like for some of like for Halloween's or for doctors, like you have confusions in these spores, right? So do you think like depth can be one of the
that's what I meant by using 3D spatial data from the this one. So yes, we only tried it with two-dimensional data, and we're going to be using three-dimensional data.
Mm-hmm. And like another thing, maybe like you can use some kind of attention mechanism, like for the first questions like that Vito asks, that like how do you like try to like work on like if you have a different like background or illuminations. So maybe like some kind of attention mechanism like could be like a solution for those things, filter out the feature and to get a better representation. Hello.
Yeah.
Okay.
Yeah,
Okay.
I
So
think, yeah.
Mm-hmm. Okay, so let's thank all the speaker and clap them virtually. And this was a very nice session that we had. So we'll go for like the next keynote. And I think we are running out of time. So I'll ask like the next session chair to hand over the next keynote.
Thank you very much, Abhijit. Let me introduce our next keynote, Lisa Anthony. She's a tenured associate professor in the Department of Computer and Information Science and Engineering at the University of Florida. She got a PhD from Carnegie Mellon University in Human-Computer Interaction in 2008. And her current research focuses on understanding how children can make use of advanced interaction techniques and how to develop technology to support them in a variety of contexts. She had previously received an NSF career grant, among other industrial and governmental grants, and her work has been recognized by the research community with 4 Best Paper Awards, including one in 2013 at the ACM Chi Conference. So Lisa, the floor is yours. I think you can share your screen now. And you're still muted, by the way. I'll ask my, I will stop our videos.
Can we see my screen and
yes,
hear me now?
Yes, now it's perfect. Excellent.
Great. Terrific. Hi, thank you everyone. And thanks Albert and the other organizers of the workshop for this invitation. It's an honor to be invited to speak with all of these other illustrious keynote speakers on the topic related to human behavior understanding. So I think thanks for that. So I'm going to talk to you today about some of my work over the last 15 years on understanding, designing, and developing natural user interactions for children, especially as it pertains to the topic of today of human behavior understanding, focusing on really how we understand what natural user interactions children might generate and how we can support those. I'm gonna make sure my screen's advancing properly. So I've been doing a lot of this work for the past 7.5 years while I've been at the University of Florida with my lab, the Intelligent Natural Interaction Laboratory. And this is a picture of some of my research students before COVID back in spring of 2019. So we focus on child-computer interaction as our primary application domain. And our main goal is really to help users, especially children, interact with advanced natural user interface modalities like touch, gesture, whole body motion in ways that are going to really support the needs, expectations, and abilities of the users themselves. So instead of just creating algorithms that we think might work, we really look at how the users expect them to work and how we can make them work better to recognize real input behaviors. So like many people who are working on multimodal interaction, we're aiming to help these users be able to interact naturally with technology in a way that does not interfere with their primary task. Often, the goal here is then to use natural interaction behaviors based on prior experience with human-human communication or interaction with the physical world. So if we can sort of model and emulate those types of interaction behaviors, it'll make it easier for users to learn how to use those interactions. That's our primary goal. So to achieve this kind of natural multimodal interaction, our research takes an interdisciplinary approach. On the one side, we're investigating foundational questions of what kinds of patterns or behaviors we see in users' input. If we know something about what users will actually do, we have a better chance of building a natural user interface that can interpret their input correctly. And here's where we spend a large focus on understanding natural human behaviors so we can model and recognize them. On the second half of the picture is the development side. In order to interpret the user's input, natural user interfaces have to use intelligent recognition algorithms that listen and observe user input and infer the intent. But if we build these recognition algorithms informed by what we know about users' real input patterns, we can end up with a much more fluid and natural and accurate experience for the user. Both components of this type of research draw on background knowledge, skills, and methodologies from different disciplines, enabling the research to take a more holistic approach to developing new technologies. And my work in the past decade has primarily focused on touch and gesture. So today, that's really what I'm going to be focusing on. But the approach that I will describe to how we understand, design, and develop interaction for these modalities can extend to other modalities like motion and whole body interaction. And we do have some more recent work on those modalities, including data sets that I'll talk a little bit about at the end. So here's some examples of the kinds of real input behaviors that we might be looking at seeing from kids or adults when we're talking about drawing shapes on touchscreens, for example. Our current work has shown that the same algorithms don't work for kids as adults when we're trying to recognize these types of gestures. And you could probably see some of these reasons why by looking at these gesture samples for children and adults. I probably don't need to show you the labels for you to guess which were kids and which were adults, but we still have a long way to go to recognize the diversity of gestures that kids will make. So I'll reveal the answer here. Of course, the more consistent and cleaner looking input tends to be what adults have been able to create, whereas children have a higher range of variability and less control as they're creating these gestures because they're still learning, and therefore these create challenges for our recognition algorithms. So one of the ways that we try to address this type of a problem or this type of a challenge is to collect lots of data in the form of touch and gesture samples from kids of all ages, gender, academic achievement, socioeconomic backgrounds, so that we can look for input behavior patterns in that kind of data that we can then use to develop better intelligent algorithms to understand kids' input. So as an example of the range of touchscreen gesture behaviors we've seen over the years in our studies, this is a set of gestures from our data set, all from the same 5-year-old child. You can see that even the same child of this age writes the same shape in widely varying ways across multiple examples, which creates a major challenge for current pattern recognizers, which are really going to be expecting fairly consistent input. It can tolerate some variance, but not the level of variance that we've seen with kids. So currently I've been working on, as I mentioned, primarily touchscreen interaction for kids has been our primary modality. And there are three sort of phases that the whole talk of our approach, that the whole talk is organized around: understanding, designing, and developing. And when we're talking about understanding, we're really that's really where the human behavior understanding component comes in. We really want to understand how kids are using touchscreens in their everyday life. What are their patterns and how they make gestures? How and when do current recognition approaches not work? Because that will expose those edge challenge cases that we would have to focus on in developing new algorithms. And so in the developing side, we are then looking at new algorithms for understanding touch gestures, and also tools that are going to help developers analyze input behavior patterns so that they can choose the best gestures for their context, or the best recognizers for their users in the context. And the third aspect is really to put all this together into applications that can make use of these algorithms and provide touch interaction support for kids. And primarily, a lot of our work has been in educational context. So I'll talk a little bit about that near the end. So today, I'm kind of going to focus more heavily on the MAGIC project, spend a little bit of time on the gesture tools, and then mention only briefly how our work has been applied in the TIDES project. And that's sort of to reflect the emphasis of this workshop on understanding human behavior, which is really that first part of our approach. So I'll talk a little bit about the MAGIC project now. So the MAGIC project stood for Mobile Touch and Gesture Interaction for Children. So for those paying attention, the T is silent. And we ran this project over 5 years. We ran 6 studies with kids and adults, over 120 kids, primarily focusing on ages 5 to 10. Early results that we had in our studies early on, a wider range of children all the way up to high school seniors, but we saw that the most difference in kids and adults' behavior occurred during those primary school years. And by the time they were in middle and high school, their input behaviors looked a lot more like adults, and therefore maybe they didn't need as tailored of approaches. We also looked at kids in school rather than kids that were before school, because of the types of tasks we were looking at, like writing, things that they would have needed to have some exposure to in school, but to be able to participate. So to talk a little bit about the types of tasks that we had them do, on touch screens, on your iPhone, on your tablets, you're probably doing 2 primary types of things. You're doing gestures that could include creating shapes or doing navigational gestures, and you're touching targets, on-screen widgets, menu items, things on the screen that you have to touch in order to activate them. So our 2 primary tasks focused on these interaction models. And they're really focused on the basic atomic interaction. So we isolated the input behaviors from any effects of the user's context or the task by just providing these really simple stimulus response-based interfaces that we instrumented to capture all information available about the user's touch behaviors. So as they tap the screen, all of the information that the hardware and software could log about that touch interaction would be logged. Things like the XY coordinate, the touch pressure on some devices, the touch size on some devices. And on the gesture side, we captured the XY coordinates and speed and timestamps of all of the touch events that made up a gesture, so we could then use that in the recognition process as well. So these were the simple interfaces. We also later explored whether or not visual complexity in the interface affected interactions for kids. A lot of kids' games are going to have a lot more things on screen than the simple interactions that I just showed you. So we created these little games that would sort of see whether the same relationships held when there were more visual components to the interface, or if the interactions really could be isolated. I think if these videos will play, you'll see you'll see some of these. Oh, it's not going to play. That one, let's see which ones it will play. So it can play 2 of them. So these are just showing you the in progress of a study, someone interacting with the targets and the gesture apps to be able to complete our tasks and provide us with the data that we need. So to kind of highlight over all of the years of the project, the main findings that we uncovered about kids and their touchscreen interactions, we saw consistently throughout all of our studies, children missed more targets than adults. So when they were trying to acquire a touchscreen target, they tended to hit outside the bounds of that target a lot more often than adults would. The smallest targets actually were the most challenging, which might be counterintuitive. If you think about a small finger on a child, maybe they could hit a smaller target, but it turns out that dexterity of acquiring that target, the precision needed, was the dominating factor. So larger targets were better for kids. And children's gestures, as I've already shown you, were much noisier than adults, both within children, their own samples, but definitely across children and across ages. And all of these effects were magnified the younger the children were. So 5-year-old children exhibited all of these behaviors, these inaccuracies and noise much more frequently than even 10-year-olds would. We also saw that visual complexity of the interface would make kids miss more often. So we hypothesized that they're maybe distracted, or it's harder for them to do the visual search through the interface for the target that they were supposed to be acquiring. And recognition algorithms don't work as well for kids' gestures. Even if you train the algorithms of the time on kids as training examples and test on the same kids, they were still doing 20 to 30% more poorly in accuracy than they would for adult gestures. And finally, although another major theme that we saw was, although everyone tended to come to our studies and use their experience on iPhones and iPads and other touchscreen devices and apply them to their experiences on new touchscreen platforms in the lab, like larger tabletops, spherical displays, which I'll talk a little bit about later. Children and adults both use gestures they would have already used on those platforms they had experience with, but children were much more likely to try unique and unexpected gestures to navigate or control this interface that the software wouldn't respond to. And so that's one of the challenges, would be to understand how to either support those new gestures or at least create a situation where the application doesn't fail gracefully. It would fail gracefully for those types of interactions. So just as an example of the kinds of data that we collect in our data sets and how we went about analyzing for some of these patterns, here is an example of a touch cloud generated from a target acquisition task. The outline is the phone screen and the XY coordinates are labeled. And basically that little cluster of touches represents all of the events recorded for one study for a target in that location, the little black outline. The red squares are the children, where the blue triangles are the adults. And adults also miss. This is one of the smaller targets, but the children miss a lot more often, and the children's misses are more dispersed than the adults. So this kind of data set can be really helpful for us to understand not only the raw information about failure and success in interaction, but also the parameters of that behavior, the degree of tolerance that we need to design our interaction recognition algorithms for, and how we can better support kids to be successful in these types of interfaces. So in the spirit of sort of thinking about human behavior understanding, I think one of the really most important parts is to be able to model and understand their behaviors, including collecting these data sets of the wide range of behaviors that they might exhibit. In our MAGIC project studies, we've collected a lot of samples. over 55,000 touch events, 35,000 gestures from children and adults. And we've made these data sets available for other researchers to analyze and use in their own research. And we really think that by having a few benchmark data sets like these, more researchers can work on understanding human behavior and building recognizers for it without having to expend the effort of collecting their own data sets, especially for users that are less common, maybe less accessible, like children, for example, which people often ask me, how do we run all of our studies with kids, which I will talk about in the next slide. It's not as hard as you think, but it still does take time and energy, and having these data sets be more widely available increases the access that people have to do research on this type of problem. The Magic Touchscreen data set we have is by far the largest data set that we have. It's certainly the largest that I know about for touchscreen interaction in kids. We also have some other data sets in whole body interaction and speech for kids, like I mentioned before. So one of the main questions I often get asked when I talk about my research and our lab's research is working with kids. What are the, isn't that hard? How do you get permission? How does this work? How do you have access to children? That kind of thing. So there are a lot of challenges for sure to collect data sets from kids, and especially when you think about balancing the need for control so you get systematic data that's useful and helpful to you for machine learning experiments, but also natural and reflects real world behaviors from kids. So, we do a lot of work that involves empirical studies, where we did all of the MAGIC studies involve bringing kids to the lab where they interacted with our technology, and we recorded all of their data so we could combine it into the data set. And this is definitely something where you have to think about things like attention, study length, motivation, the environment that you're running your study in, trying to make it cheerful, less like an institution. And we did a lot of work early on to try to create protocols that would improve our chances of being able to get quality data from the kids without deviating too much from what their natural behaviors would have been. So some of our early work, we started adding these things like gamification elements. You might have seen in the video, and it's shown here on the screen with the penguin. We had scores and points. Everyone got the same points and everyone got the same score. Just by doing the task, you were getting points. But the kids enjoyed that as a motivating element, and it kept them going through what might have otherwise been a tedious data collection task. We also provided prizes for completing the parts of the task, which we called levels. And we allowed children to choose the prizes that were the most motivating to them. In terms of attention, we also steer away from conducting sessions with children who know each other, because they start to become competitive. If you're going to do multiple kids at once, they become competitive, or it sort of changes their dynamic in a way that might affect your data. And one of our early papers, Brewer, that appeared in Interaction Design in Children in 2013, we showed that the use of gamification increased our study completion rates by kids ages 5 to 10 from 73% in the plain, no score, boring, simple apps to 97% when there was a score. All you had to do was add a score, and then they were much more excited to keep going and playing the game, which was really just collecting the data for us. So I'd be happy to answer any more questions people have, maybe about working with kids in studies in research in the Q&A session. But I wanted to move on now to talk a little bit about how we then take our understanding of kids' behaviors in touchscreen interaction to develop both tools that help us analyze those behaviors and also algorithms that might help us recognize their interactions more accurately in the Gesture Tools project. So developing touchscreen gesture tools kind of has two parts that I lump into that category. One is our gesture recognition algorithms. You may have heard of the dollar family of recognizers. started by Jake Wobrock with his $1 recognizer that I'll talk about a little bit on the next slide. We've extended them later to more robust and fluid algorithms that would be able to tolerate higher variances in behavior of how people might actually make gestures. And the way that people make gestures, we called articulation. So how they articulate the gesture by drawing the shape on the screen. And we provided tools to help researchers and designers analyze their articulation behavior patterns of the users that would be using their app. And that would help them see, oh, I shouldn't pick these two gestures are often confused for each other because of how people articulate them. So therefore I'm going to, maybe not put both of those in my app and that kind of thing. So I'll talk a little bit about the dollar family of recognizers. Jake's $1 recognizer was first created in order to show that we could program simple, fast, accurate accurate recognizers and only handed unistroke, one stroke at a time. Like you didn't lift off your pen from the paper or your finger from the touch screen while you made the gesture. That's why in the picture for $1, the X is connected, because that was just a simple and fast recognition approach. But with kids, you are going to have a lot more variation in how they make gestures, and you're not going to necessarily be able to get them to learn a new gesture language to draw shapes on the touchscreen. So we started looking at extending that out into ways, an algorithm that could support multiple ways and natural variation in the articulation patterns. And so that first led to $N, which kind of brute force represented all possible variations of how people might make a two-stroke gesture like an X. And then P$ became the most robust and the one that could handle the most variance by not considering order of strokes at all, but just matching point clouds to point clouds and allowing the users to articulate their training examples and their testing examples in any way that they naturally might do. And although these algorithms weren't created with kids in mind, they were created with the desire to create more and more robust algorithms that could handle wider variations in user articulation. And since kids tend to have a high variance in user articulation, the ones, P$ ends up being the one that's the highest accuracy for them for that reason. And so for those who aren't familiar with the dollar family approach, it's a really simple template matching based approach that just involves some pre-processing to your shapes. So this is a 3 that has been resampled, resized, translated, and rotated so that you're hopefully finding the optimal match between the training template and the testing candidate that you're trying to recognize, and just computing the Euclidean distance between subsequent pairs of points. And the match score is the sum of the distances between these points. And the lower that scored, the closer it is, and therefore the more likely it is to be recognized. So the more templates that you have, the more variation in user gesture articulation behavior you can recognize. So unlike machine learning approaches, which need a lot more training examples and can tend to overgeneralize beyond small nuances of articulation that turn out to be important to capture, the template matchers keep a lot closer to the original user articulation and therefore can do a better job in some cases at recognizing those variances. So it's an interesting point. This sort of simple approach can actually be quite powerful. With only a few training examples, you can get very high accuracy if your users are very, very consistent. If they're not very consistent, you need more training examples, but you still can yield very high accuracy with relatively few examples. So on the other side of things, besides recognizing the behaviors, we also develop gesture analysis tools that would help us analyze how users made gestures. We originally thought that this would help designers and researchers do two things. One is understanding variation in user behavior, and therefore perhaps helping you select the gestures to include as in your application, but also it might inspire algorithms or approaches to helping people understand users' gestures better, helping algorithms interpret them better. So these are 3 tools that we've developed. The gesture clustering toolkit, which basically focuses on finding commonalities in how people create a gesture, what are the stroke orders and directions that are the most common, so we can make sure we provide support for those in our application. The gesture relative accuracy toolkit focuses on really understanding the range of user behavior by measuring how far user articulations are from a set of canonical articulations or the average articulation. And then GHOST is the gesture heat maps toolkit, which kind of shows a similar set of things as GREAT, except overlaid. This is sort of a heat map showing where the hotspots of variation are in articulation for specific gestures in a data set. And all of these tools are available online for download for researchers and designers to use in their own work on specifically touchscreen gestures in these cases. So in this particular thread, I've already mentioned gestures from children are much noisier than adults. Recognition algorithms don't work as well for kids. We also saw that through analysis with our gesture tools, the younger the child was, the more noise, the more challenge their gestures created for algorithms, and the more variance we saw when we looked at them with our tools. And therefore, recognizers needed much more training examples for younger users. So they needed more for kids in general, but they also needed more for like 5-year-olds than they did for 10-year-olds, just because you need to capture that range of variance that kids might generate. We also saw that through some of our studies, adults can recognize children's gestures better than algorithms can. So there's something that we're doing as humans that we aren't quite able to get our algorithms to tap into yet. I think in the adults, the study that we ran where we asked adults to recognize children's gestures from our MAGIC data set, they got up to 91% accuracy, whereas in our machine algorithm accuracies tended to be on average more like in the 80 to 84% range. So at the best case. So that is really showing that there's something more. Like it's not just that children's gestures are so noisy that we'll never be able to recognize them, but we still have a way we can go to capitalize on whatever the adults were using. And we're still looking at doing that in our future work. So for example, of some of the findings that I mentioned in specific, I mentioned that children's gestures show higher degrees of variance than adults. This is all one 8-year-old. Actually, this is a range of 8-year-olds drawing a circle. I think every column is a different 8-year-old. So you sort of see the range of types of things that you might need to be able to capture. And the other interesting finding that I wanted to highlight was that young children show even less consistency than older adults. So if you look in general, the lighter the heat map, the more variance there is. And there is just more variance in general for 5 to 7-year-olds. But if you look at the 3 circle gestures, the plus, the arch, and the arrowhead, you really see a stark contrast to where the variance occurs and how even between 5 to 7 and 8 to 10-year-olds, the consistency increases for the older children. And so that would mean you would be able to get away with fewer training examples. We are also looking at ways to capitalize on the parts of the gesture that kids are more or less inconsistent around, like transitions and stroke beginnings and endings and intersections, and maybe de-emphasizing those in the recognition process so that we could increase our accuracy to be better for kids' gestures. So in my last couple minutes, I just want to mention the kinds of things that we can do once we have this understanding of natural touchscreen behaviors from kids, what we can do to actually use those in real applications. So a more recent ongoing project, we were funded through 2019 and are still working on the project, is called TIDES, Touch Interaction for Data Engagement with Science on Sphere. So here's where we've been able to work with some exciting new technology, spherical displays, which are a lot different than flat screen displays, but they're touch enabled, and they really have a lot of power for representing global data sets, interactive exhibits for learning in science centers and museums. So our overarching goal on this project was to understand what people want to do and what helps them learn better in these touch-enabled exhibits. But we are also using what we know about how kids and adults use touchscreens differently to be able to create more accurate interaction experiences, so that the software can respond better to the kids and the adults in the museum setting, and therefore create a stronger learning experience for them. So we started by working on flat screens. We've been expanding that to spherical displays. And I could talk a little bit more about that if people are interested in the Q&A. But basically, this interdisciplinary research that we've been doing, my collaborator is a science educator, has been helping us to design effective learning experiences for these new form factors based on what we know about how kids are touching targets on the screen and how that may or may not need to change when you're looking at a different display factor like a sphere. So just to wrap up, I want to leave you with this image again, and I have another slide about some of our future work, but just the idea of how these two halves of the coin really work together to inform our research. We can't develop new intelligent algorithms, in my opinion, without thinking about what the user needs and capabilities are that are going to generate their input behaviors that we need to recognize. So this interdisciplinary work really, I think these two halves of the coin are not separable in the type of research that we do. And over the next 5 to 10 years, I see my lab expanding into some of these other modalities. We already have speech and pose whole body motion data sets that you can check out on our website. And we've been also looking at how kids understand intelligent interaction. What do they think of when they think of the machine recognizing their input, and how we can combine some of these modalities into multimodal input and interaction for kids as well. And a key assumption that we've been making so far is that a lot of those existing methods that I've talked about with collecting data sets and designing tools to help us understand the input behaviors are going to transfer well into other modalities like speech and whole body motion. And I thought it might be interesting to just think about, especially in the theme of human behavior understanding for kids, where I think some of the interesting challenges are going to be in the future. So as we've seen, a lot of new technologies are emerging. A lot of times children and any other special population are going to tend to be behind the curve in terms of supporting their interactions on those technologies. The first problem is always to get the technology to work, invent the technology, and then we're thinking about the typical user that's just anyone's average, every person type of user, without thinking about how the range of input and interaction behaviors is going to change across all people, but certainly for populations like children and other special populations. So I'm interested in thinking about future challenges like deformable displays for children, on-body displays, certainly zero display technology, mixed reality for kids is a big future challenge, I think, in understanding how it can work for them. And then primarily I've talked mostly about children that are neurotypical and physically able, but there are lots of challenges to think about with respect to motor or vision impairments, developmental or learning disabilities for children, and how it might affect their interactions with new technologies. It might change the very nature of their physical behaviors with the technology, that would then affect the recognition algorithms that we use to try to understand and provide an experience for them. And then, of course, in keeping with the sort of theme of a lot of the talks today is multimodal interaction, beyond touchscreens, speech, whole body, gaze, on both input and output side, and using multimodal interactions together in a continuous stream. And how would that be different for children versus adults? So that's all I was going to talk about today. Thank you so much for your attention. If you have any questions, feel free to follow up. Here's a shot of my current lab pre-COVID and some of our funders and acknowledgements to the institutions that have supported us throughout all of our work. Thanks so much.
Thank you very much, Lisa. Let's have a round of virtual applause for our speaker. I have a bunch of questions, but let's see whether somebody from the audience, do anybody have a question for our speaker? Vito, please. Yes.
Yeah, thank you, Lisa, for the very interesting talk. So I have a question. I have two sons, one is 9, the other one is only 3. And so even the smaller, so the little one, when he sees the older brother interact with touch devices, he also wants to use phones, tablets, whatever there is, right? So what's the age distribution of children that you work with? So are you also looking at really little ones, or so what's the general range of age that you consider for these types of experiments?
For our MAGIC data set, the kids range from ages 5 to 17, and then they're mostly in 5 to 10-year-old range, because that's where you see quite a bit of development. While the kids have been introduced to school and are starting to learn to write, motor skills change a lot in those years. Now, certainly motor skills change a lot between 0 and 5, but we have looked a lot more at the post-school age so that we can kind of take advantage of the fact that they've started to learn to write. We did recently do a study that included 4-year-olds, and some of the very same relationships, exhibited themselves. So I think that what we've seen is it's really a linear trend in general. These challenges just become more and more significant the younger the child is. And so, I would recommend, the younger the child, the bigger the target, the simpler the gesture. Most likely for kids that are, not ready to write, the shape-based gestures might not be successful at all. I think there's an age where, they can start to make lines. Maybe some navigation gestures are possible, but pinching and zooming and rotating, those types of gestures are really challenging for kids with developing motor dexterity under the age of 5. So I think there's just a lot of interesting work that could still be done in those age ranges.
So maybe just as a follow-up, so when you work with these children, I guess it's challenging to make them do things, right? Do experiments with them. So how does it look like? Are the children accompanied by parents, or they do come in alone, or do you want them separate from the parents? So what's the overall setting when you collect the data?
In general, I think it's challenging, but probably less challenging than most people think. I mean, the kids, are used to, if they're in school age, then they've had some type of school setting. So they're used to adults in the authority. And what I always tell my research students is to sort of put on a cheerful persona and, be excited to be there, and the kids will be excited to be there. We try to decorate our lab with colorful objects. It doesn't look, like a boring lab if we can help it. And one of the things that we do with parents, we kind of give them the option. Most parents actually don't mind letting the kids be in a room with us or separated. So we've done a lot of different things. One is we'll have the kids and the experimenter at a table while the parents are at the other end of the table. They're kind of not part of the study. Other times we've done things where there's an experimenter room with an observation window and the parents are on that side. So the kids know they're there, and the parents can see them, but the parents aren't affecting how the kids will behave with the technology. I think the younger the kids are, the more you have to provide parental support. Another thing that we've done a lot is not necessarily in the lab, but in after-school programs where the kids will be pulled out of the program to do our study. So it's not exactly a lab study, but it's also not exactly a natural environment study because they're still doing these types of tasks that are artificial. But again, the kids are kind of used to that model, and therefore, as long as the parents have provided consent in advance for us to pull them out, we always double check with the kids that they're still interested in participating, and then we can go from there.
Yeah, thank you. Very interesting work.
Thank you.
Abhijit?
Yeah, thank you, Lisa, for a very interesting talk. So my question is that, do you think like some way of like volunteered like data collection, like volunteering giving the data connection, or like a multi like participant based data collection that can help like to have like more like better data, like just like gamification?
Sure. Well, there's already been some work in doing that in general, not for kids, but there's I think it's the Million Touches project where they basically deployed a game on the iOS app, on the iOS store, and people downloaded it and knew that their data was being used for research, but it was, collecting a very large sample of natural touchscreen behaviors. So you could do the same kind of thing in a game for kids. And we've thought about doing that. I think if, we were to move into some of these other populations, like maybe children with motor impairments, it would be more difficult to recruit them locally or from one school. We would probably need to have a broader recruitment strategy. And so maybe putting it on the App Store, making sure, of course, that everybody knows that the data is being captured anonymously, but it's still going to be stored and analyzed. That might be a good way to reach a higher degree of saturation for populations that are more difficult to recruit in person. And certainly now with COVID, and none of us are doing, well, at least none of us at my institution are doing in-person studies for, things that are not saving lives, like playing with touchscreens isn't saving anyone's life. So our human subject studies have been suspended. We could do online studies like that. That would be a great substitute.
Okay.
Thank you.
I think Benjamin has a question. Benjamin, would you like to open your video and ask? Okay, so then I'll read. So he's asking, would you say there's a correlation between, for example, normally developed 5-year-olds and older handicapped children? And could your findings be easily used to facilitate user interaction design for other groups of people, or is it more complicated than that?
That's a really interesting question, and one that we often get is, whether we can identify equivalency classes of user groups. And so, for example, a lot of people think, well, if kids are developing their motor skills and older adults are declining motor skills, is there some type of correspondence that you could see? I can actually say in the older adult case, I had a student group do a project in a class that never was published, but they did collect data from older adults doing these same types of tasks. And they did have, they had more variance in their behaviors, but not nearly as much as children, and recognition accuracy was just as high as for 18 to 49-year-old adults. So I think those types of things are interesting to explore, but you really need at least a small data set to be able to show that equivalency. And so I think an interesting future work could be trying to develop a set of features that have, easily classifies based on a small set of samples, the equivalency class. So you don't have to collect a lot of samples from one person, but a few samples, figure out which algorithm, which recognizer that's tailored to a certain set of variants will work best for that user, and then go ahead and start using that in the application. I think that would be really interesting future work.
Yeah, a related question to that maybe. So when you look at the errors made by children, then you can see, for example, what kind of motor skills are there missing, like keeping a straight line, keeping a constant curvature, or joining the fine edges. And if you place these errors in a developmental trajectory, for example, you could possibly create a system with which you can synthesize examples with these pathologies. So you can, for example, still collect your data from adults, but then distort them in certain ways that will conform to the types of variants you would see in different age groups. And then you can have access to a lot more synthetic data to train systems with, without ever going to the kids. I mean, we're looking into similar things for children's pose estimation, for example. I mean, we have here in Utrecht University a study which is called the Youth Cohort, which follows 3,000 families from birth onwards. And then we're dealing with very small kids interacting with their parents. And the common pose estimation tools like OpenPose, etc., they don't work very well. And it's very difficult and very challenging to annotate real data. But if we can have, for example, synthesis of these things, perhaps we can, fine tune these generic models to deal with children's data a bit better.
Yeah, I think that's definitely a possible interesting avenue. And I know there's been some work on data synthesis for touchscreen gestures in specific at the University of Central Florida with Joseph Laviola's group, for example, and some other work. So, I think that could be something where if you have a seed data set, then you can generate a random range within certain models parameters of what the variance could be. And so really just having enough of an idea of what that range of variance is important. So you need some type of base data set to help you start that process.
Yeah, and some of the examples that you've shown, replicating some geometrical shapes, reminded me of the tests psychologists use to diagnose ADHD, for example. A classic example is, a circle and a cross within the circle, and then your ADHD patient would draw the circle and the cross separately, not inside. So the relationships between the primitives are mixed up. So is this kind of, have you ever worked with ADHD kids? Can you, for example, use these kind of techniques for diagnostics? Does that make sense?
Yeah. We haven't worked with any kids with ADHD in our lab. There's some work going on at the University of Florida for patients with stroke rehabilitation, doing those types of diagnostic tools that we've partnered with to help them build apps that can score those types of tests. So I think we could apply a very similar approach in the kind of case you're talking about. If there's a diagnostic test that exists, then it's fairly straightforward to make that a digital version that you can then score. But you need that basic ability to recognize variance and understand what measure the variance, and then report the variance in terms of what the diagnostic output should be.
Thank you. Satish has a question. Satish, would you like to ask it yourself? Or I can read. Okay, microphone issues. No. So the question is whether you can do biometrics with this kind of data. For example, let's say you ask the kids to draw certain patterns, and then can you re-identify the patterns drawn by a particular child?
Yeah. So there are some potential solutions you could look at there. We have done a little bit of work on using touch and gesture interaction for biometrics, only very early stage stuff. And typically, I think there's some challenges with respect to memorability. So what gesture is it? The more unique the gesture is to the child, the more likely the biometric will be successful in identifying them. But because if you're using something like a circle, I don't know that we've seen enough variance to be uniquely identifying the individual with that. Although it depends again on maybe the age of the child or the context. And so there are a lot of challenges that I think we didn't address in the current work that I presented, but that could be looked at. There are some folks who've looked at gesture passwords for kids in the interaction design and children community. So that might be something that would be of interest to the person who asked the question. And I think, you know, there's a lot of people who are interested in how to create experiences for kids that are just as fluid and natural as for adults. People think, you know, kids are going to jump into any interface and sort of be a digital native and hit the ground running. And to some extent, they're willing to experiment more than adults. So they do sort of become more fluent sooner, but there are still a lot of challenges that they experience with not getting their intentions recognized. So I think there's a lot of interesting open space to still be explored, both in this modality and in all the other emerging technologies that we're still going to need to consider wider users and human behavior variation when we're looking at those technologies.
I have to admit that the spherical display that you have shown, I have never seen before. So to me, it's really interesting. Is it at the moment a commercial system already, or is it?
It is a commercial system. The sphere that we have is produced by Pufferfish Limited from the UK. There's also a group in Canada that's been working on like a cheaper version, a DIY sphere, so to speak, for much more affordable price. But because the commercial system is quite expensive due to basically the projector that's inside and the computer that runs it. It's actually not technically complicated, but it is the optics, you know, can be expensive to create a high resolution enough display to be interactive. So that's what we've been lucky enough to be able to work with on the TIDES project. And we're looking at continuing that work in the coming years.
It's really interesting. Thank you very much.
Thank you. Thank you so much for the invitation.
If there are any other questions, we still have a few minutes. Otherwise, we can have a 5 minutes break because we didn't have any breaks before. We can have a 5-minute break before the next talk. All right. Thank you, Lisa. So,
thank you.
Thank you.
So, Louis-Philippe, if you want, we can test the connection and in the meantime, but yep, the screen is there. Okay, but we can't see you. And,
yeah, we can.
Yeah.
Yep.
Yes, I can see you and you're muted. Wow, that was a good zoom. You have a fairly advanced camera, I suppose. You're still muted. And is that Amsterdam behind you?
Yeah, in your honor. Every time I have a meeting with someone else, I change I put a different one. No, I like that. I have a really good souvenir of Amsterdam.
Nice. So, in which city are you now?
In sunny Pittsburgh.
Oh. Is it cold now? there?
I'm Canadian, so it depends what you call cold. It's very warm, I think, but
maybe we should
if
ask
it's not
for one.
minus 20 Celsius, then it's very warm. So everything is relative. I like winter. Winter should have snow. I mean, holidays without snow is not one of the holidays. So, but I'm biased. I come back in 1 second.
Yeah. Okay, so let me introduce our next speaker. Louis-Philippe Moranci is a Leonardo Associate Professor of Computer Science at Carnegie Mellon University Language Technology Institute, where he leads the Multimodal Communication and Machine Learning Laboratory. He was previously a research faculty at USC Computer Science Department, and he received his PhD in computer science from MIT Computer Science and Artificial Intelligence Lab. He's one of the leading researchers in multimodal interaction, and his research focuses on enabling computers to analyze, recognize, and predict subtle human communicative behaviors during social interactions. His research is very multidisciplinary, spanning fields of multimodal interaction, social psychology, computer vision, machine learning, and AI. Louis-Philippe was the general chair of ICMI 2012 and the initiator of some of the most most appreciated traditions in the ICMI community. He was a program chair in 2014 and 16, and he also chaired the ICMI steering committee. And today he will talk on multimodal artificial intelligence. So Louis-Philippe, the floor is yours.
Thank you for the great and inspiring introduction, Albert. Yeah, so I want to talk today about a passion for me, multimodal, and now specifically multimodal AI. If I have to say, from all the great work that has been happening, specifically in the last 5 to 10 years in multimodal, I'm primarily interested in when it's human-centered multimodal. How can we have computer understand subtlety of human communication? I'm blessed to have very great students and collaborators. My group is interested in multimodal, the AI, the core, how do we do the algorithm, but I'm also interested on the human communication side and also the mental health. I will talk a little bit about the others, but I will focus primarily today to share about multimodal AI. A lot of what I will talk about today is in fact also inspired by a course I've been teaching now almost for depending how you count it, 5 to 10 years. So I also invite you at the end to give more details. But we're in a world where technology are not only understanding unique modalities like speech or vision, and language, but are becoming more and more multimodal in the way they interact with human or even sometimes interact between AI systems. We see it with mobile phones. Mobile phones now these days have many sensors in it. Cameras and keyboards are only one of them. There you get a lot of interesting physiological sensors on some of these smart wearable. And so we're at a point where you get all this heterogeneous data. If you ask me what is multimodal research, at the most global sense, it's really the study of heterogeneous data. And we see this happening also even more these days. I mean, multimodal, we're in the world of multimodal, probably more than we want, spending days and days in front of video conferencing. So then you ask yourself, how do we improve these technology? How can we make them, in a sense, more useful, more perceive, really good at perceiving. And so that's the kind of things I'm interested. Personally, I study 3 modalities. I call it the 3V of communication: verbal, vocal, and visual. What you say, how you say it, and also the facial expression and gesture that goes with it. There's a lot of information in the selection or the choice of words you make, but we know that these can be put together into phrase, and these can also change the meaning from that. And also when you talk, it's not just about the semantic, but it's also the intent behind the words. The biggest example are sarcasm, where the word themselves may not be as exact to the intent that was defined behind it. So this is the aspect of verbal. And then vocal, there's at least 2 aspects to it. The prosody, which is related to the words that are spoken, their intonation, the voice quality, but also the vocal expression, like pause fillers, laughters, for example. So these are the verbal and the vocal. Visual is also close to my heart. I originally started in computer vision, although I identify myself as multimodal. I come from the computer vision world. And so gestures are important. B gesture, eye gestures, and a lot of this is in the body language, the posture. Proxemics is a little bit harder to express, or at least visualize through web conferencing, but definitely in face-to-face interaction, very important. If you ask me, one of the first cues I often look at for face-to-face interaction, it changes when it's video conferencing, but face-to-face interaction, I believe that eye contact and eye gestures are very key to interaction. That's often one of the first cues we look at. And very important and probably most publicized, and great talk earlier also on the topic of facial expressions. And as we've seen, not only the basic or facial expression, which have been seen or observed across a different culture, but looking beyond that, like engaged or distracted or confused are the kind of states that also often express themselves through facial motion. So this is our goal. This is kind of the input. This is and if you ask me, what are you going to do with all of these AI technologies that analyze heterogeneous data? My biggest passion, and goes nicely with some of the work that was just discussed by Lisa, is healthcare. Healthcare is one direction that I'm very passionate about. And there's many reasons for that. And probably most of you know or already understand the importance of healthcare, but specifically mental health. 1 in 4 adults will experience mental health in their life. And this is the #1 disability in the world. So this is very impactful research. And we're not just, my goal personally is not about creating an AI doctor, a doctor in a box. That's not my goal. My goal is to build technology that help and support the healthcare provider, the human, the doctors that are there. And so we want to build technology that if the human is interacting with their doctor, or we're in the 21st century, maybe they interact with a virtual interviewer. I call them virtual interviewer. The person, the virtual interviewer there, is not there to make a diagnosis, but just to gather information. And as they interact with them, then technology like the one we're building, a Multisense, will gather. And one of the aspects that's really good with AI is that they can be objective in their assessment. And so that allows us to give some objective measure of the person multimodal behavior. You could almost see it as the goal of doing, if you think of physical healthcare, like a physician, a physician, when they will want to confirm their intuition, they will often go and ask for some exam, like maybe a blood test, and look at the percentage of cholesterol, for example, and use that to make their assessment. That's a little bit the same intuition, is that now we want, but this is for mental health, and we unfortunately don't have those blood tests. But if we look at the interaction, we can look at these markers, behavioral markers, that can then be shared with the clinician. It's almost seen as the blood test of mental health, and then use that so the clinician can either confirm their intuition or maybe gather some more, or realize that there's more questions to be asked. Use that to eventually share information with the patient. And what are these? I personally, we want to look at behavior indicators, or sometimes we'll call them behavior markers or biomarkers. These, what they are, is that they are a quantification of the behavior of the patient. This is a quantification, and that quantification has a few important characteristics to make it a behavior indicators. One is they're contextualized. They're contextualized in the interaction. So contextualized by the type of question that the healthcare provider or doctor or clinician were asked. And also they're linked very directly, at least empirically, where they're linked with behaviors, they're linked with mental health disorder and symptoms. And that's really what's important, is that now we have a quantification of the patient, and then we can see the computers can give this information on a regular basis. Maybe the person comes every week, meeting with the clinician, and then we can see the progression over the time. And if we're lucky and we have a nice corpus of other people that were recorded, we can also look at this as a reference. And that will give us our behavior markers, like how is this person today? Is there a lot of variance in their behaviors? And where are they compared to this norm or norms, what's often called norms, statistical norms? And so that's the kind of behavior markers. This talk today is not on the details of these behavior markers. I'd be happy to give another 1 hour talk just on this topic. We have more, over the last 11 years of work on this topic, we identify a dictionary of behavior markers, and these are initial research that identified them. So I think we have about 24 to, depending how you count, 24 to 28 of these behavior markers. These are quantification of the behavior, either verbal, vocal, or visual, that have been seen to correlate with symptoms of depression, psychosis, including schizophrenia and bipolar, and suicidal ideation. We also look at anxiety and PTSD, which I didn't show there. The kind of behavior markers are sometimes like more intuitive, like smiling. You will expect someone who smiles less often when they're depressed. It's quite interesting because it's not just the smile that's often important, but it's dynamic, because the smile often of depressed will have like shorter smile and less amplitude. But what I find also really interesting is that there, for example, in psychosis, is that there it was the language, very important, the structure of the language, the selection of the words. So, and one of the aspects of schizophrenia is that this really interesting switch between thoughts. And so what you will see as maybe grammatically okay, but you will look more carefully and you see these are unusual series of phrases. And that's kind of one example of a marker for schizophrenia and psychosis. You can implement or operationalize this with something like a language model. And suicidal ideation, another example, was to predict when someone is going to do reattempt in suicide ideation. Someone goes to the ER and you'd like to be able to predict, is there a likelihood of them reattempt? Like maybe the first time was a first ask for help or cry for help, but like which one is the, and it turned out the voice was a cue. It was one behavior marker, not the only one, but it was one interesting behavior marker. And it was interesting that someone really tense were in somewhat less likely, but someone with a more breathy voice that maybe have made their mind was a bigger behavior marker. The core of the research and the talk today is about integrating all of this information from the different behaviors. How do you bring together verbal, vocal, and visual in a way maybe to build some kind of technology to assist? And here's an example. This is using interpretable machine learning, which also means something very close to statistics usually. That's a keyword that you often hear. But here, what's interesting here, it was a population of 100 patients, and what I find interesting in this is that you not only can see here in blue the assessment for that person. So this is, and we rank them like, so people here are more likely to show sign of depression, and them less likely. And this is the normal cutoff on those self-report. And the green is the accumulation of verbal, vocal, and visual and doing an assessment level. And these, again, we should not see it as making a diagnosis, but mostly as an early screening kind of scenario. I think this is. And so the goal now is to how to integrate that. How do we build multimodal machine learning algorithm that integrate all of these into heterogeneous data? And so this is my passion. And when I started, when I started on multimodal almost 20 years ago, there's mostly two options when you do multimodal machine learning. Early fusion or late fusion. Either you aggregate your features early on, learn one classifier using an aggregation, concatenation of all your modalities, and then predict, or late fusion, where each modality tries to predict your class label, and then you have a simple either majority vote or some aggregation scenario at the end, late fusion. What's really wonderful of the last 5-ish years is that we've seen a lot of progress in multimodal machine learning. And this happened in parallel with deep learning, deep neural architectures. And so as you look at all of this work, it's interesting to try to kind of categorize, what does it mean, multimodal machine learning? And this is our attempt, my attempt in our group my group to try to identify 5 core challenges in multimodal machine learning that are core. They're maybe not the only one, but they're definitely core in being able to integrate heterogeneous data. I sometimes make this joke that if you have problem falling asleep tonight, this is a wonderful paper for you. It's slightly old in the deep learning world. I will call it an old paper of 2017. But what's really nice is these challenges identified more than 3 years ago are still very relevant and not solved. There's still a lot of interesting work to be done there. And so I would like to identify with you some of these challenges and also some of the more recent work in each of those 5 These is work in my group, and I'm also very happy, and I will give you a pointer at the end to a full course on multimodal machine learning, where I not only highlight the work I'm talking about today, which is this talk today is primarily about my research group, but also the course is a lot more, very little about our group's research, but primarily about all the work, the great work that happens in the field. But the first one is multimodal representation. Multimodal representation is this challenge of how do you take this heterogeneous data, verbal, vocal, and visual, it could be physiological, medical sense, like imaging, medical imaging. How do you take all this heterogeneous data and find a way to learn a representation, in such a way that you explored complementarity. What is like useful to bring together so that I, in fact, with the two pieces of information, I get to learn something new that was not in itself in each of them. You really needed complementarity between them. And also, very important, look at redundancy. What is the information that is the same in both? Some of more recent work, I don't have a pointer in this talk today, is to look at it in an information theory perspective, and also looking at mutual information. These are key aspects of multimodal representation. So the goal at a high level is, how do you bring it into one joint representation? This is one way. I'm going to talk about the second way of doing this, but the one that is the most popular is doing joint representation. I bring all of this in one joint space. And I had this goal, and I think we're getting closer. This was a dream that I had a few years ago, and I think we're getting closer. The goal is to have this joint multimodal representation. So that if I say I like it, I'm joyful tone, I have a visual facial expression that show happiness, that they will be close to each other. If it's a tense voice, very close to each other, or surprise, close to each other. These are the kind of things that you would like this joint representation to do, where even if observation are from heterogeneous sources, they should still, if they have similar meanings or similar intent, or represent similar information, that they should be close to each other in that joint space. And so when you do this joint representation learning, the basic way, which is getting closer to, I would call early fusion, is to just concatenate these. So you take information from text, image, and audio, and simply concatenate, and then using a few layers of neural network, learn this joint representation. And this, if you are interested in doing multimodal machine learning and would like to have a data set like for multimodal 101, sentiment analysis is a good place, is a good benchmark. I think by now, I will not call it the only direction you should go, but I think it's a good place to start. Our group offered many data sets in that, and there have been some extension, including some great one about bringing multimodal and social interaction as well. But yeah, so sentiment analysis is a great way to start. But even with something that has been studied like sentiment analysis, there's some very interesting challenges when you look at multimodal representation. And one of them is to look at the interaction between modalities. What are those cross-modality interaction? And so if you look at sentiment, there is a first type of interaction, which, or you could call it lack of interaction, but it's unimodal interaction. It's within a modality. There's always interaction within a modality. So this movie is sick as a phrase. This movie is sick may be ambiguous. It could be in US seen as positive, in other culture may be negative or ambiguous. This movie is fair. It could be neutral or slightly positive. Smile by itself is a dynamic that shows that is likely to be positive, although as we see in talks, smile is not always positive, but it is a likelihood to be positive. Loud voice. Loud voice can be ambiguous. I can be loud and positive. I could be loud and negative. So there's ambiguity there. But this movie is sick and I smile, now you're a lot more positive. This movie is sick and I frown, a lot more chance of negative. This movie is sick, I loud, very ambiguous still. And that's what we call bimodal interaction. Two modalities comes together and has complementary information, and when bring together, they give a better assessment for the task, or at least give better representation, more informative representation. But then you have this movie is sick, smile, and loud voice. And this one is very strong, but this movie is fair. Even if I'm loud, I smile, or fireworks in background, these often doesn't bring as much, because in this case, language takes over. And that's a very interesting nonlinear interaction. It's as if all the example I gave was just additive, like I'm just adding adding things together, then my problem would be very boring at the end. It's just add evidences from each modalities. But there are nonlinearity, and you need to be able to model that. And so this is why for this, people have looked at first at bilinear models. Bilinear model is the idea of multiplicating the two. So you have a representation of X, like your text, and Y, and you just do a bilinear products between the two dot products. And then what you get with this is then a nice matrix that looks at the interaction between each modalities. This gives you for each dimension of each modality, how they interact with each other. It's a simple representation, but quite powerful. And you can do small tweak to that. That's what we call tensor fusion network, where you add a little one into it. And there, what's nice is not only do you get this bimodal interaction, but you also get the unimodal interaction in the same tensor. In the same tensor, you will get both the unimodal and the bimodal interaction. And there's nothing that stops you from doing, example here, the trimodal interactions as well. So this is an example where understanding the problem and the representation can help creating better representations. And if you're concerned, which was one of our personal concern for a while, about the complexity of that, there are ways to not creating the full tensor that can be highly dimensional. There are ways to create the composition of the problem and rearranging things in such a way that you become linear with the number of modality. So this is an example of joint representation, but that goes beyond just the plain joint representation where you put all your hope on neural networks and just hope that you have empirically enough data to learn the relationship. Here, you're kind of using a little bit of domain knowledge and expertise to try to design models that takes into consideration unimodal, bimodal, and trimodal interaction. This is what I talked about when we talk about joint representation, but I'm also really interested in looking beyond just like bringing everything in one joint space, because sometimes one modality may not be, should not or may not need to be fused with the other modality. For example, my shirt has a certain texture, the sidewalk has another texture. Linking or grounding this texture with language can be a very, it will take a lot of words to express the subtlety of this texture. And so when I'm really joining language and images, I may not want everything in a joint space. There are information from the images that are just visual, and they're useful. They're still useful for the task, but they may not necessarily have an equivalent that's called in the NLP world, natural language processing, they use the term grounding, where language is grounded into something else, often is in images. But in a more generic term will be alignment. That's the term we use in my group, is alignment. So this like complementarity or alignment between modality may not be for every aspect of an image. And maybe not all aspect of language has a link with the image. There may be some aspect of grammar that are very specific maybe to that a specific language, English or French, or that has less of a link to the other modality. And that's why it makes sense to have coordinated representation. So you have two representations, one for each modality, but you find a way to coordinate it. It's not the strongest coordination. Strongest coordination means you want them to be completely equal, which mostly becomes joint representation. But no, you want to coordinate them. And one way to coordinate that I would call very strongly, but still is different than just making them equal, is to say, hey, I want them to be correlated. If one is increasing, the other one will increase. They may increase in different direction, but I want them to increase both. And you can make it in a canonical way to say there's more than one way they can be correlated. They can be correlated because maybe sentiment is in both modalities, but they could also be correlated maybe because of culture or because of a number of people. So then you have many canonical bases to your space, and then you want them to be correlated, and that's where canonical correlation analysis is an example to that. In this case, I just show it in 1D, where you want them to be correlated as much as possible. When we're learning those representation, either joint representation or coordinated representation, I believe, if you ask me, one of the big challenge moving forward is not only learning these representations, but also really being aware of biases. And biases can come in many different ways. One is just data set biases, and in the fact that the data set has a certain size. I think it was one of the questions earlier today about like the size of the data. And so implicitly, if you don't have a good representation of everything, every possible, you will probably are likely to have biases in that. And these biases, some of them may not be harmful, but some of them could be quite harmful. And so we want to be able to identify these biases and create technology to be able to study them and maybe even reduce their impact. Removing them maybe one day, but at least in the short term, identifying them, I think is the key, and reducing them. Removing them maybe later, but let's start one step at a time. So research question is that there's been great work on language representations, and there's been some initial data set that give us some tools to assess biases in language model, for example. But the question that I think is really ongoing is how to do it in multimodal representations. And I'm seeing a few there last year example in that, but there's still very interesting problem. That's something open question that I leave to all of you, including researchers, but also PhD student or graduate student. The second, technical challenges, and I will say what really makes something really unique of multimodal machine learning is alignment, like the grounding between modalities. And I personally believe that's a very interesting aspect, because you have elements from each modalities, and you want to be able to know how do they synchronize, how do they link, how do they ground to each other. These have been used, these terms, grounding, alignment, and synchrony, all used in that kind of, we call it, I personally prefer the term alignment. And there is two types of way when we look at the challenge of alignment. Is one is make the alignment explicit. My goal, my loss function is to find that alignment. Like, I want to know what words relate to what object in the image. I want to ground all of these words. That's what's called explicit alignment. Implicit alignment, try to do the alignment, but it doesn't have supervision. It has it indirectly. It will have it through some other task. So maybe you do image captioning, you do another task, which requires, almost every task in multimodal requires alignment. But the task may be a translation like image captioning, but implicitly, intermediate step, you will need to do it. And so you may want to translate between modalities, like visual modalities. I'm interested in looking at how do we align between verbal, vocal, and visual. How do we align with these three modalities? And one of the approach for that, what we would like is to be aligning then so that because I may say a word like it's huge sort of spectacle movie, but I may not do the visual behavior exactly like spectacle, maybe relate more to something that I said just or behave a lot earlier. So if I align things just based on what is happening now, like what is it, like kind of a synchronous alignment, then I may lose some very useful information. And so this is why how do you model asynchrony in modeling representation. And now, although it's only 1 year old or almost 2 years old, but the transformers or self-attention models are one way to approach this, where what you will do is I want to be able to align all visual and all vocal and verbal together. But as a step to that, what I will do is say, how can I visually contextualize the verbal context? As a first step, I will say, hey, the word spectacle, what does it relate to? How is it the most similar? And I'm going to learn, it's going to be part of my process, is to learn those similarity function. At the core attention, those self-attention model, if you ask me, one of the core component of self-attention and transformer is that similarity function. Because it projecting in a space, and then in the simpler transformer just do a dot product. I personally like to see it as kernels, like really learning how to best learn a similarity function. And if you are successful in learning a good similarity function between modalities, then you can go and take these embeddings and say, hey, what is in the visual that is not yet in the language? And that's why you have a residual connection in most transformer architecture, because then suddenly you get this new visually contextualized representation of language. And if you do it in all possible bimodal interaction way, then you get new contextualized or better aligned representation. And these are coordinated representation. And there's you can do then over multiple layer, and you can always decide if you really want to create a joint representation. So what I talk about right now, and that's very a core of it, is representation learning multimodal with joint and coordinated, and the challenge of learning alignment between them. I want to say two more challenges, and these are probably the main one I will talk about given the time. One is, okay, all of them, heterogeneous data, you need to do representation learning, you need to do alignment, but then what do you do after that? And then there's two branches. Either you do translation or you do fusion. That seems like 95, 98% of the work is either translation or fusion, is often one or the other. In translation, you go from one or many modalities to another modalities. And I call it translation because the parallel is like in machine translation, when you translate, like say, from English to French, but here you translate, for example, from an image to a language. This is different conceptually to fusion, where you bring modalities together, not to create another modality, generate another, but to infer something about these modalities that is higher level, often like example, like emotion recognition from what I say, how I say, and how I behave. So translation, image captioning, wonderful topic. It's another multimodal 101. If you want to start on something MS COCO and machine translation, I'd like to give you example of other type of translation. One example is language to pose. So the best example for language to pose is now, so you don't see me anymore, but you hear me. And so you've seen me for 30 minutes, so you probably have a good idea of the kind of behavior I'm doing. So the idea here is, can I learn from 30 minutes of interaction to animate this, and then could use it to later on. So language to pose will be the goal of language and speech to gesture. A simpler version of that is called narrative to pose. There, I narrate, I say the character walk and then slowly talking and decide to leave the road. This is a narrative. It's slightly easier, but I think really interesting, and that can be helpful. And so one interesting is that narrative to pose, where a person walk in a circle and you want to merge it with motion. And motion, you want to make it so that maybe motion looks similar, but they are semantically different. And that's why it's important to not just learn separate model and separate space. You really want to learn a joint space in this kind of situation. And that way you can learn just from language how to animate a character. So you dictate. And you could imagine using it to a robot or something like this. But I may also want to use this. Oh, I thought I removed one of the slides. Sorry, I had an example also animating characters. It seems that I cut it because of time. But you can also use language as a way to describe the kind of object. So you say, hey, I would like to go and you pick up a toaster at the store, but I'm looking for one that is broad, is silver, it has 2 slices. And so suddenly you're giving your instruction to your AI assistant, and you wanted them to be kind of internally build a recognizer of that and be able to do that. It could be a toaster or could be animated. And you could also use language to tell them where to go, give instructions, go to the entrance, lounge on the left, and all this. So all of these are examples of translation. I want to talk about fusion. I'm very passionate on this topic. Fusion is the idea that you take these modalities and now build and recognize something more like that's common to all of these. And so example of that is the sentiment analysis. And I want to give you 2 strategies for fusion. There are a lot more, but I would like you as a take home to have 2. One is about fusion as a memory process, where what it is you've been listening to me right now and you don't remember everything I said, but there are a few times where you're like, oh, that's an interesting piece of information. So you attend at that point, look at local evidence, and then put it in your memory. And then later on, you may find another piece of evidence and then link it to what you talk about. And that's the idea of memory fusion. But these and most of the fusion technique that exists all suppose that all modalities are born equal, that they're all as important. But in some cases, you know that one modality is much stronger. Let's say for sentiment analysis, you know that language is a very important modality because sentiment was originally designed as a linguistic phenomena. So there, instead of making all 3 of them there, you will say, hey, language is important. My other modalities are only going to be there to shift the language estimate. And that's called, we call it shifting or multimodal adaptation gate. And that's the M-BERT, multimodal BERT idea. If I had more time, I will also express to you the co-learning into this, which is about the idea of using one modality to help the other modalities. And so if you want, again, tonight, falling asleep, wonderful paper survey. And this fall, thank you, pandemic, I recorded my whole course online. So there's now almost 15 weeks of video lectures on this topic, all available on this website and on YouTube. So you're very welcome to look at this, and happy to answer any question. Thank you very much.
Thank you very much, Philippe. Let's have a virtual round of applause for our speaker. It's not the same, but yeah. Okay, so we're ready to take questions from our audience. Yes, Vito.
Yeah, so thank you, Luis Philippe. It was a very interesting talk, very interesting. So I was wondering, in your first part, you talked about mental health and automatically diagnosing, or let's say provide support for clinicians. So my question here would be, we had a, let's say, related project that was also looking into things like that. So from speech, and the medical part, so the medical community here was not really forthcoming. So what's your experience in terms of clinicians? How willing are they to adopt such technology and include it into their daily routine? So, or maybe a more important question first would be, is it even mature enough to be applied in clinical use?
Yes, this is very important. I will say when we started 10 years ago, very few people were in the clinical world were ready for that. Now there are conferences ran by clinicians on this topic. There's quite a few of them. There's one at Harvard, the TIP one, and there's a few others that came, for example, from internet-based technologies that you see there. It's all about the claims. When I started, I did the mistake of like, hey, I'm doing a diagnosis machine. I'm doing a diagnosis. That's the wrong way to approach it. I think it's decision support. And you have to think about it, the right use cases. And I think personally, the first one is probably going to be in treatment, because there you see the same person over time. And so then you can look at changes over time. I think that's a more likely. But the other place where really the healthcare community want it is in screening. They see a lot of people. They see a lot of people, and then they would like to be able to find early on cases that maybe the general practitioner for some reason didn't pick up on it, or just want to confirm some things. So I think getting the right use cases is one. Getting the right collaborators has been the challenge over the years, but I believe there is now enough of a core of it that there's enough momentum in this direction. But I'm still looking for, like, sometimes they would like to have that killer app and all this, and like, oh, that one example that showed that we helped so many people. We're not there yet. So I think a lot of these collaborations are based on belief that this technology is going to have an impact soon. My guess is we're probably in that junction point that if in the next 5 years we don't get this, we're going to lose momentum. But I'm a believer that in the next 5 years, we'll start seeing some of it, not solving it, but enough to get an impact. But if we don't get it in the next 5 years, then we're going to take then a different shift. We're going to shift a speed, like in self-driving car now. We're not going to solve it by 2021. So I think we've been a little bit more careful than the people in self-driving cars. We didn't say everything will be solved in 2021. But still, I think the next 5 years are important now to try to find a few of those use cases. So.
Yeah, I see. I agree. Thanks.
Louis-Philippe Gaurav is asking whether this has been applied clinically or not. And as a medical doctor, he's asking, how can my organization participate in this type of processing?
Yeah, no, that what I found the best collaboration is definitely on one side is flexibility. First answer, yes, it's been applied. My collaborators are McLean Hospital, if you know, in US, that's the biggest one for mental health. But what I found is you need to have, it takes time. And people and clinicians are very busy, extremely busy. So you need to be willing to take the time for that. Data is important, but what I found the most important is contextualized data. So data where the clinician and the researchers work together to try to develop a protocol that will bring behavior markers more likely, where like they're more likely to come up. If you just want, hey, I have all this bunch of data I recorded for another study, we may be lucky and it worked. But I think in the short term, we want to work together because there's a lot of knowledge about those disorders where there's intuition for depression, for example. We know there's positive and negative affect that are very important in depression. In schizophrenia, we know that there's a lot about, is it about myself or is it about someone else? There's a lot of difference on that perception of reality. And so you want to be taking that information and make a protocol that will bring the behavior marker more likely and also allow to contextualize that. So I think in the short term, that's the right path. In the long term, I would love to get any data and I magically get a quantification. But I think in the short term, it has to be a close collaboration.
Yeah, also sometimes I suppose the medical doctors have intuitions that can point out to new behavioral markers that we start to investigate computationally. And those are, for me, very interesting cases. In one example, we had some collaboration with the Alzheimer's Institute in Turkey, and they had this suspicion that Alzheimer's patients look younger than their age. So we collected a data set, and that took us 1.5 years, but eventually we were able to show that yes, actually their smile dynamics, their age appearance was actually, they appeared younger than their supposed age. The automatic age estimators were underestimating their age, but now it's, it can inform diagnosis, perhaps, and it can even turn into a tool like Louis-Philippe is mentioning eventually, maybe for early screening, for continuous monitoring, maybe, and things like that.
Yeah, and a lot of this intuition, I see Sydney, who is ready to give a wonderful talk. A lot of these intuition also come in the education world. You can't look at behavior markers without some understanding of the theory behind it. I think that both inform both ways. And so I'm new to the world of learning and education, the one of mental health and healthcare. I know a little bit more, but yeah, your intuition, Albert, is perfect, right on.
I have a small question about the different modalities. What we often experience is that some modalities have a lot of data gaps. For example, if you're monitoring, let's say, an interaction within a room with a therapist and a patient, you may not catch the face, a lot of times. If you're using a single camera, maybe 10% of the time you can see the face, and then there will be a lot of gaps. So how do you deal with this for all these multimodal, actually cross-modal maybe, representations that you're building, that you're integrating?
Yeah, I was debating, I was that close to include all the cool stuff we're doing right now on AI and machine learning. A lot of our work is on robust, being able to robust on partially observable or noisy data. That has been a core of our group in the last few years. One example, for example, is the deep gambler work and some of the follow-up. That was a NeurIPS paper. Because here you want to be able to, maybe you're lucky and you know that something is not observable. That's one category. And then one modality is it's partially observable. And then the deep gambler is more like, what do you have confidence on? And one of the things that I like, the idea here, the reason I talk about the deep gambler is that I can talk about it in one sentence. The idea is that you want to predict a class, but you also allowed to just say, I don't know. You're allowed to say, I don't know, but you're not allowed to do it too often. And it's a little bit like gambling. Gambling is like the horse race. I mean, if you never put money on any horse, you're never going to get any kind of reward. So you need to sometimes bet, but you want to bet only when you know it's good. And so this is just one example. There's a lot of interesting related work in that. So that's one direction of I'm interested is like, I call it self-aware AI. It's okay for AI to be wrong. I expect AI to be wrong sometime. And in fact, probably most of the time, but as long as it knows that it's wrong, I think it has to be aware that it's wrong. And that I think is a very important aspect of, and we can't put any kind of technology in healthcare or education and learning without handling that self-awareness. And I think that's important. That's related to your question, Albert, of also missing data. But missing data, I see it as not slightly easier, but a stepping stone towards that harder problem, which is fully, you don't know when things are there or not. Like if you know that it is, you don't see the face, you just know that it doesn't fit, but sometimes it's just noisy. So the noisy case is the hardest, and there's the one where there's occlusion. And I think this spectrum is very interesting of like robust AI. And so I think, yeah, robust multimodal AI. We have a few papers in my group. I think it's an area to push forward into that. Like, if you ask me what are the most important, and that's probably the last comment because I'm taking too much time. Robust is important. Fairness is extremely important. Interpretability are those three directions my group is taking these days. Robust, fairness, and interpretability. Yeah. I should have a slide about this. Sorry.
So I would have asked you about what you think about Yoshua Bengio's consciousness-related models and how this kind of metacognitive skills implemented in neural networks in relation to your answer, but I'm not going to do that. We have little time. Giulio is asking, commenting first, one standard way to deal with bias is to have a balanced data set. And then he asks, can you comment a bit on how you deal with this problem when different modalities of data are considered?
Yeah, I think there's two different. Yeah, we may have a slight different definition of biases, but yeah, unbalanced data sets are true in many scenarios, and I think it goes, I will say, to the what I would call more limited resources. I think it comes down to we have limited resources, and we want to learn from limited resources, and there's no magic way there. There's no magic. If you have just very limited and nothing else, the best thing you can do, and I personally like very much, is domain knowledge. Like, what is it? Expertise. That's one path. I think the place that we see interesting words on the self-supervised learning world or unsupervised learning that comes and help us there. I think we can see something there. I don't know the solution for limited resources. I'm very interested in that topic. We don't study it as much in the short term. We've been studying those three things that I mentioned. I know that limited resources is going to be important in the future. We work right now by evaluating our process very well. And I think having a bias is just, I don't want to remove that. I mean, like, I don't think it's going to be possible to remove all biases. So instead of that, I prefer to work, and that's when I call fairness, or I could not call that line of research biases, is just to identify them. And I think that's very interesting and unsolved. I would like to remove them eventually, but just identifying them will be a good first step. Yeah.
Thank you very much, Louis-Philippe. I think
Thank you. Thank you very much.
The next talk. Thank you very much. And I leave the space to, I think, Vito, are you going to be introducing?
Yeah. So thanks again, Louis-Philippe, for the interesting talk. And we move on to the last keynote of the day, which will be given by Sidney DeMello. So I'm very happy that he accepted our invitation to give a talk. And I'll just shortly introduce him to everyone. So Sidney is an associate professor in the Institute of Cognitive Science and Department of Computer Science at the University of Colorado Boulder. His work lies at the intersection of computing, cognitive, affective, social, and learning sciences. He's interested in the dynamic interplay between cognition and emotion, while individuals and groups engage in complex real-world activities. He has co-edited 7 books and published more than 300 journal papers, book chapters, and conference proceedings. His work has been funded by numerous grants, and he currently serves or has served as an associate editor for 6 journals. He served on the editorial board of 4 others and was selected to the leadership team of 3 professional organizations. So very happy to have you here, Sydney, and please proceed with the talk.
Should we stop recording?
Yeah, so maybe just as a note to everyone, so this talk will not be recorded. So if you're not here, you're gonna miss it.